In this series, we're building up a small computer on the breadboard using the Motorola MC14500, which is a 1-bit microprocessor. So it'll probably end up being the slowest and least powerful computer on the planet, but I think it'll be pretty fun and pretty neat. Last episode, we ended up building a clock built out of 555 timers. And so what I want to do this episode is I want to take that clock signal and pipe it into something else. Most notably, I want to build the program counter. So let's hop over to the bench. We'll take a look at the Motorola handbook, how they suggest of building the program counter. And then we'll take a look at the chip that we're going to use, and then we'll build it up on the breadboard and give it a test. So let's hop over there and get started. So this is the minimal ICU system that we're trying to build. And not shown on here is the clock that we ended up building in the last episode out of the 555 timer. But now that we have that clock signal, we can just start building this, and I'm going to go from the top to the bottom. And starting at the top is the program counter, which they're using the MC14516. I don't have any of those, so instead I'm going to use a 74HC163. This is a CMOS level pre-settable 4-bit binary counter, and I'm going to use 2 of them just like they have set up over here to give us 8 bits. Now pre-settable means that we can load in a 4-bit number to it and then it'll start counting from that number. But the MC14500 handles jumps in a really interesting way. Really inefficient way, I guess, would be a better way to explain it. Instead of trying to jump to a different spot in the program counter, what is far more common through the material that I've been reading is to essentially just turn off the input register or the output register and just let the program counter make another full loop. Super inefficient, but it means that it's going to keep a little bit of our setup for these binary counters a little easier. So if we take a look at the pinout of the 74HC163, you can see that we got this P0123 and the Q0123. So this is going to be our inputs for loading and our outputs for the binary number that we're outputting. And then we have a bunch of other ones: MR, CP, PE, TE, SPE, TC. That's a lot of stuff that we're going to have to think about how to hook up. But fortunately, in this data sheet, there's this handy little chart back here that shows what each of these inputs or outputs does and how to set them up to achieve what we want to achieve. So we'll just keep this in mind while we build it up, and hopefully Bob's your uncle. So let's pull out the breadboard and get started. All right, so here's where we left off last time with our 2 little 555 circuits over here, and these should still be working. Yeah, there we go. All right, so we have a working clock. I'll just unplug the power here for a second, and then we'll build the program counter over here on this half. So first things first, let's get the 74HC163 in place. All right, and I've placed these so far apart because the outputs are all up here on the top, and ultimately they're going to have to swing around and come back down this way. So I left enough space here for the 8 outputs to swing right on down through the center here. All right, now first things first, let's get power and ground set up, and power is going to be pin 16 and ground is going to be pin 8. So next we'll take a look at pin 7 here, and that is a count enable pin. And so we need to just pull it high all the time so that the chips can count. Okay, and then the next 4 pins, pins 6 through 3, are going to be our parallel load inputs. And so we're not going to use those at all. So I'm just going to tie all of those together and then tie them to ground. All right, and then pin 2 is the clock input and pin 1 is the master reset. So both of those need to be tied together for both the chips. So I just need to run some jumpers that connect those 2 together from there to there. And for now, those are just going to stay hooked together, and we'll deal with hooking it up to the clock as well as figuring out a reset, which I want to kind of put here in this empty space, a little later. Moving over to the other side, pin 9 is our parallel enable input, and it is active low. And since we're not going to load anything, we want to pull it high. All right, and then pin 10 is the count enable carry input. And so we use this when we're cascading. So when this one gets up to counting to 16, or 4 bits of 1111, the next one we need to clock this and tell it to count. And so we have, that's what this input pin is for. So on this first chip, since it's going to have our least significant bit on it, we're just going to tie it high. So essentially so that it's always working. Now for this chip, the count enable carry input, which is pin 9 here, it needs to receive something from here. So there's another pin that's an output specifically for that on this chip. And so we need to run a long jumper over to this area so that we can dig into that output coming out of this one. Now that jumper is a little too long, but we essentially want it to come back over to a pin over here. Now the pin's kind of in an inconvenient spot. The terminal count output is pin 15, so it's this second to last pin here. And trying to get pin 15 over to here, I didn't have a jumper that was the right length, so we're going to go past it and then come back to it. There we go. It's kind of a roundabout way because we come out of pin 15 back over to here and then up and then all the way back over here. But that'll get it done. Now pins 11, 12, 13, and 14 on both of these chips are going to be our outputs, but they're kind of organized in a weird way. So the least significant bit, which is going to be Q0, is on the left side of the chip, and then it goes Q0, 1, 2, 3, and then Q0, 1, 2, 3. So really we want the least significant bit to be all the way on the right and the most significant bit to be all the way on the left. So that would be Q3 needs to be all the way on the left side, Q0 needs to be all the way on the right side. And so we need to run a strange collection of jumpers in this narrow spot here to arrange all 8 of those right here in the center. So I got some jumpers here and I'll just run those right quick. All right, so that's both of our counter chips set up, and ultimately we'll end up running some lines from these 8 inputs down this way to be used later. And I also want to run some LEDs on here so that we can see what the count currently is. But before we get to that, I want to set up both the clock input and the reset over here. Now for the clock input, I would like to be able to flip a switch and halt essentially whatever stage that we're on, separate of whether the clock is running or I'm pushing the button. Essentially just cut the clock off from these chips. And there's a lot of probably much better ways of doing this, but I'm going to do it with a 74HC163. 00, which is a quad 2-input NAND gate. So there's 4 2-input NAND gates on there. So that's what this guy is right here. All right, so we want to hook one input of our NAND gates up to the clock input over here. So I've got a little jumper to do that. And the other input of that NAND gate we want to run to just a little switch so we can essentially toggle the hold on and off. So that's what that little switch right there is going to be. And we're going to run the center pin of that switch over to the input for our NAND gate. And then one input of that NAND gate is going to go high, and the other input of that NAND gate is going to go low. And we'll go low through a little 1000 ohm resistor here. That way, whenever the switch is in the left position here, we're counting up, and whenever the switch is in the right position here, we've essentially halted. Now the output of this NAND gate is going to be inverted from what our clock is. And so we want to re-invert that so that we can send in a normal version of our clock over to these chips here. So we want to take the output of this and we'll run it into 2 inputs of another NAND gate. So we'll do that with this little jumper here. And since that output goes to 2 inputs, we got another little jumper here. All right, now the output of this second NAND gate is the clock input that's going into our chips over here. And if we remember, the clock was pin 2. So I've got a little jumper here that's going to go from pin 2 over to the clock output. There we go. So now we have a halt through our 74HC00 here that is controlling the clock that's being input into here, and the clock is being input into both of these. Now we still need to hook up our reset, which is pin 1, and it's actually an active low. So we want it to be high unless we push a button which pulls it low. So we're going to run a little jumper from pin 1 here over to this final kind of open space that we have here. All right, and I want the reset button up here. So we're going to run a little jumper to move that line up to here. And then we'll just use a little push button like we used for the clock on that one. All right. And then on the same pin of that clock, we're going to run a 1000 ohm resistor to our plus voltage there. So that way we have essentially 5 volts coming through the resistor, through the jumper here, all the way over to our reset here, holding it high. And then on the other pin of our clock, we're going to run a jumper to ground. This way, whenever we push the button, what we're essentially doing is we're taking this side of the resistor and pulling it to ground. And so that'll also simultaneously pull the reset to ground, which should reset both of our chips here. And I just realized, fortunately now, before we had everything hooked up, that I forgot to hook up power and ground to our 74HC163 here. And so power and ground are going to be pin 14 and pin 7. So let's hook those up right quick before we turn it on and we don't know why it's not working. There we go. And there is one final jumper that I do want to hook up. And if you remember last time, we took our clock signal and we ran it over to one of these extra rails that we had on the end. And so I want to do the same with our reset signal. I want to run it over to one of these spare rails. So I've got a really long jumper that we're going to do that with, but it has to kind of run underneath my potentiometer here. So we'll just lift the potentiometer up slightly. All right, so that should be everything except for the fact that we can't see the output. So I want to run some LEDs off of this, but to have both a resistor and an LED and 8 lines being output to someplace else is not easy. We're running real tight on space. So what I've done is I've taken these LEDs and I've soldered on a resistor to one leg. So you can see that I've got the LED pin here that comes out through a 10,000 ohm resistor here. Now, 10,000 ohm resistor is massive for these LEDs, but like the blue LED over here, these green LEDs are really, really, really bright. So to keep them from blinding me, I'm using a large resistor. But this should let me plug them in just like that, not have to worry about having a current limiting resistor for the LED. So let's go ahead and get all of those hooked up. All right, and as you can see, it's kind of a tight fit. They're really smushed up against each other, and it's really kind of hard to get all of these stabbed into the correct place. One last thing I want to do is that it's always good to have a little capacitor on each of the power rails there. So I'm just going to stuff a tiny little capacitor into the power rail there to kind of help fight noise. All right, that should be everything. So let's hook power up and see what happens here. All right, well, we've got something displayed on there. Let's hit the clock and see what happens. Yeah, it seemed to count up a bit. Interesting. So if we hold reset and toggle the clock, yeah, that resets it. So let's just let it run. Oh, hey, did you see that? That was interesting. So we're not... Oh, it counted over that time. Weird. I'm getting some interesting issues here. Sometimes the carryover count works and sometimes it doesn't. Now this could be because I forgot to take pin 15 here to ground because it's essentially a floating pin. So let's try taking that to ground and see if that changes the behavior any at all. Interesting. Our last LED didn't light up here on that one either. Ah, I see what's happened here. Okay, we got to pull all these LEDs out on this side here because I got them off by one. Okay, so all of these were off by one pin this way. So we were displaying the top 3 bits on these 3 bits here, and the top LED wasn't hooked up to anything. So let's give this a shot now and see what happens here. We'll reset it. See if we get our carryover. Yeah, that works. Let's speed it up a bit. Yeah, there we go. Yes. Oh, that's super cool. So there we go. We have an 8-bit program counter here that's putting out essentially an 8-bit address that our memory module should be able to read. So that's awesome. And let's check the halt. Yeah, there we go. Okay, so you can see our clock is still ticking away here, but we've halted it. And then we can just pick right up where we left off. Awesome. All right, so everything is working. And it turned out that the biggest issue was just that I wasn't able to stab the LEDs in the right spot. So that works brilliantly. All right, so this is super cool. I'm super happy with this. So in the next episode, we'll figure out the memory module. But for now, thank you guys so much for watching, and we'll see y'all next time.